All right. Can you guys hear me? Test, test. Can you guys hear me? It should be fine, right? All right. So let's get started. Okay. Just give me one sec. I'm going to track it here. Okay. So let's get started. So welcome, guys. Welcome to our Alex Ivy School. We are an educational organization which provides extensive trainings and coaches for North American math competition, including but not limited to American math competition like the AMC, AIME, USAMO series, and Canadian math competition such as the COMC, the Waterloo math competition, the Euclid, so on and so forth. And today is an open course. And this course, we're going to focus on the 2024 Waterloo Euclid math competition. All right. And the language for today's presentation is going to be in English. 今天我们只说英语, okay? The language will be in English. All right. So before we get started, we jump to the Euclid. We always like to spend roughly maybe 5 to 10 minutes try to answer some very important questions. There are some popular questions, students, parents keep asking me regarding the math competition. So let's try to spend maybe 5 minutes talking about the Euclid. Try to understand how the Euclid math competition works. All right. So the Euclid is actually a math competition which contains 10 problems, and each problem worth 10 marks. You have to finish them within 2.5 hours. So each problem, generally speaking, you should have multiple parts. Could be 1 part, 2 parts, 3 parts. And especially for question number 1 to question number 5, they are fairly easy problem. They won't ask you for too many sub-questions. But from question 8 to question 10, they are considered to be relatively difficult problems. So therefore, they will definitely ask you ABC 3 parts. And more often than never, you have to remember whatever you get from A part should probably be useful for the B part and C part. Whatever you get from A part and B part will be useful for the C parts. So that being said, whatever you learn, whatever you get from the previous parts, you'll be able to directly apply them for the following parts. Okay? So it actually contains 2 types of questions. For one type, it's just like a simple answer. You just give me an answer, that's it. Well, the other type is you need to show your work. Okay, a simple answer does not make sense. You have to show your detailed work. But my suggestion is, because I'm also a grader for the Euclid from time to time, I see various students. Let's say for question A part, as long as you see a little bulb, right? So you just have to give an answer. But I highly suggest you to show your work. You might make some tiny mistakes, right? Maybe some calculation error here and there. If you just give me an answer, I have no idea what you think. So if you have one tiny problem for the final answer is wrong, I'm going to deduct all the marks. However, as long as you show me the work, so, if you're just like halfway through or even 90% through, I can try to give you as much marks as possible. So therefore, my suggestion is that always, you need to show your work. Regardless, it's just like a quick question or you have to see some complicated process. Always show your work. Okay. Second is, why do I need to participate in the Euclid math competition? So generally speaking, if you want to go to Waterloo University, so normally speaking, after your application, they will send you an email and highly suggest you to participate in the upcoming Euclid contest. Of course, like the wording won't be never like, what should I say? Like the wording won't be just like you have to go there. It's more like highly suggested. But trust me, most of the students, they get admission from the Waterloo, especially for some, for the math, for the computer science. There's no exception. They all went to the Euclid math competition and all of them did a very good job. Okay. And also, if you're considered, like the entrance scholarship, definitely a very good mark from Euclid can help you, get all the way from 1,000 to 10 grants math competition scholarship. And if you go to the Euclid website, it's actually talking about the admissions and scholarships. And here it says the applicant must at least participate in one of the CSMC or the Euclid. in order to be considered admission or scholarship, so on and so forth. But trust me, they actually focus more on the Euclid rather than the CSMC. Okay, so that being said, from a practical perspective, if you want to go to the Waterloo University, taking part of the Euclid math competition is crucial, right? And talking about the certificate, here there are two types of certificate you can get from the Euclid. One is the 25%, or we always say like the cutoff score or like the cutoff certificate, means students from all over the world, as long as you are roughly 25% of the entire students, you'll be able to get the certificate. Well, there's another thing more than a regular certificate, is kind of what we call a distinction, honor roll, like whatever. So that part, you're looking at roughly 2.5% to 5%. Okay? Yeah, a student got a question, what is the difficult level of the Euclid compared to COMC? So they have different target. COMC is more target for the selection of the Canadian math competition team for the International Math Olympia. So it's more selective. Well, Euclid, it basically wants to balance the two parts. At one side, it wants to be selective. So they want to find out the talents for the Waterloo math, like a Waterloo University. Well, on the other hand, it has to give you some easy questions to encourage the students to participate. So therefore, if you check the complexity, the first 5 problems are way easy, very straightforward. All the complicated problems starts from question number 8 all the way to question number 10. So I would say if you want a rough competition comparison, I would say from number 9, especially number 9 to number 10, they are considered to be the C part in the COMC. While the previous part will be fairly straightforward. Okay, and that's the reason our lecture is going to focus on the relatively difficult part. The easy part, you can do it by yourself, right? It's nothing really special. But the difficult part, we like to show you guys the rationale, the thinking process for the entire math competition, right? And what are the problems in Euclid? They're easy, they're fair, they're difficult. So like I mentioned, there are 10 problems and each problem works 10 marks, right? So for question number 1 to number 4, or even number 1 to number 5, they're considered to be easy peasy problem. You have to do them, you have to do them right. Otherwise, you won't be so competitive talking about all the entire math competition. From number 5 to number 7, these are what I say is critical problems. So you have to minimize the unnecessary errors for these problems. If you lose a couple of marks, it's okay. But if you lose too much marks, you definitely won't be so competitive. Okay. And question number 8 to question number 10, they're considered to be the difficult problem. They're the monsters. You have to know some strategies so in order to make it right. And this is actually our lectures focus on. We're trying to teach you guys a lot of like fancy strategies here and there, try to help you guys have more exposure to difficult problems and try to know how to figure out all those common practice for question 9, question 8, and question 10. Okay. And talking about what is a good score, so this is also another question, right, that people keep asking. So like I said, if you just want to have a regular certificate, we're not asking for too much. Maybe roughly 65, that's good enough. Can help you to have 25%, okay? That's the certificate. However, if you want to get the honorship, if you want to get the distinction, you're actually roughly looking at 83 marks in order to be distinguished. Okay, so what is like the strategy to have like this 83, right? We need to have a strategy which is kind of just randomly go there. So here are the problems that you need to get the marks. So like I said, the first 4 problems, they're just like a given problem. So these 4 problems, no brainer, you have to get 100 marks, 100%, no brainer. And for number 5 to number 7, like I said, these are considered to be the critical problem. You have to minimize the unnecessary errors. So there are 3 problems. You can have maybe 1 or 2 marks deducted. So I'm looking at roughly 28 marks. Okay, you see, as long as you have these parts, you're already looking at 68. This is already good enough for you to have your certificate. Okay, But what if you want to go one step forward? You want to have the extinction? Then you have to put more emphasis on the last three problems. I'll say for question number 8 to question number 9, A part is always easy. Like I said, right? Those three problems definitely have the A, B, C, or at least the A, B two parts. So A part, definitely you have to make them right. And the B part, you can do part of them. So now we're looking at maybe 13 out of 20. At 20 scores for two problems, at least you get roughly 13, 12. And then for the last problem, question number 10, this is a very challenging problem, but trust me, most of the time, the A part is fairly easy. So compare with B part and C part, you can do roughly 2 out of 10 scores. So therefore, if you add all those numbers together, 40 plus 28 plus 13 plus 2, that's going to give you roughly 83. That's exactly what you need in order to get a distinction certificate. So this is kind of like in a nutshell, like the overall strategy, how you allocate your time in order to maximum your scores in the Euclid math competition, right? But in our lectures, we're going to give you more details, more strategies, how you can take them out, so on and so forth. And another question is, a lot of students keep asking me, what about the Euclid and the AMC? What if I just want to go to the Canadian math competitions? I don't even think about the US. Do I really have to think about the AMC? Well, the question is Euclid similar to the AMC math competition? Well, the answer is hell yes. Let's copy each other back and forth. I'll give you 2 examples without further explanations. This is problem from 2014 AMC12B, question number 21. And this is a problem from 2018 Euclid, question 8B part. Trust me, these 2 problems, they're exactly the same. Euclid basically separate the AMC problem into 2 parts to make ourselves more understandable. But these 2 problems, talking about the strategy, the solving process, is exactly the same. Another example is basically one problem from 2006 AMC10A, question number 16, and 2015 Euclid question 8B part. These 2 problems, even the graphs are exactly the same. So that being said, you always see a lot of like similarities between these 2 math competitions, and whatever you learn from Euclid can be transferable to AMC. Because the difference is that Euclid has a very limited resource. There's only 10 problems per year. AMC has 10, has 12, has A and B. They have way more problems compared to Euclid. So I highly suggest you guys to participate in the AMC, even though you just focus on Canadian problems or the Canadian like colleges, but it doesn't matter because all the knowledge, all the problems are very transferable. You can just basically copy paste back and forth. Okay. So talking about our lectures, we actually provide 2 lectures these days. So one lecture is the, what I say, it is like the mainstream lecture, is the lecture you're currently be part of it. So this is our bootcamp lecture. This is the bootcamp. So our bootcamp lecture is just try to give you guys as much detail as possible, try to cover all the important concepts you're going to be looking at for the math competition. You know, for the math competition, it basically has to 4 major parts: algebra, geometry, counting probabilities, and the number theory, right? And we're doing exactly the same for our math competition. Bootcamp. In the first 3 lectures, we're going to be focused on the geometry. So today is our lecture number 1. We're going to focus on the triangle, quadrilateral, polygons. So next lecture is going to be circle in 3D, and the third lecture is going to be the coordinate geometry. And then afterwards, we're going to use 4 lectures talking about algebra. You know, algebra is always the most complicated and time-consuming parts, right? Because we have like so many concepts for the algebra. We're going to use 4 lectures: exponents, logarithm, functions, advanced functions, polynomials, trigonometries, sequence and series. These are all the very important topics you're going to be seeing from time to time for the math competition. Moving forward, lecture number 8, we're going to go to the combinatorics. Okay, the counting and the probabilities. There's so many skills there, so many tricks here and there. We like to talk about it. in order to basically help you guys to just get rid of all those big problems. Last one in terms of knowledge session will be our number theory. Number theory will be part that not a lot of students are very familiar with. You might know geometry, you might know algebra a lot, but number theory, especially we're talking about some theorems, some conclusions, you might not see them very often in your day courses, your day lectures. So this is actually a gap for most of the students. We'd like to help you guys bridge the gap. And most importantly is that if you want to go for some difficult problems, especially question number 10, we're also offering some kind of like a boot camp for question number 10. Only talking about some difficult problems, some rare strategies, some fancy flower technologies. You can utilize some mathematical thoughts that is very common in order to solve some relatively difficult problems. So this is basically our boot camp, okay? And on top of that, we also offer another lecture. So this is what we call, give me a sec, I'm going to show you. This is what we call a crash course. You know, for Euclid, most of the students, they have a big problem is they don't know how to write the answers. If you check the official solution, the answer, oh my God, is too much. It's gigantic, right? Not to say you think about those answers. You just basically write down those answers within 2.5 hours. Most of them you do not have time. So we need to teach you guys how to shrink, how to simplify your solution while still getting all the full marks, all the marks, but without going too much details on something unnecessary. So this is more like what we call a crash course. So in the crash course, we have 8 weeks. So every day, we're going to give you one Euclid problem. The students, you can submit your solutions, and the teacher is going to give you the grading, give you the comments. And most important is the teacher is going to show you how to write solutions in a very easy way. You can see that in Euclid official solution, you might have like 2-3 pages, but in my solution, just 5 lines. But those 5 lines, every line is important. You need to show the most important thing, and you can get full marks. So I believe these 2 lectures, combine them together, is going to help you. You know, the bootcamp is more for strategy, high-level stuff, the most complicated problem. Well, for the crash course, is more focused on some easy things, but the writing process is crucial. So these 2 together is going to significantly help you improve your bet to get a good score in the math competition. All right, so that's pretty much a quick overall introduction for the Euclid. I see student got a question. Will the Waterloo engineering see your Euclid mark if you're doing it the first time this year and if you're in grade 12? That's a very good question. Okay, I'm already in grade 12. Do I still have to go for the Euclid? The answer is yes. Actually, I suggest you guys to go for Euclid as early as possible. The best bet you can do it before 12, right? Grade 11. So let's say if you do it before grade 11, you can submit your application, right? In the Christmas time or before the Christmas time, right? So you will be more like to get a early decision. Okay, ED, no problem. But what if you're grade 12? You know that Euclid always took place around April. At least you have to wait for May, the very beginning of May, to get your score, right? So in that case, no worries. Because normally what's going to happen is a lot of students will get their regular decision, RD, around the very end of April or the very beginning of May. And the reason behind this is that Euclid, actually officially give your score pretty much at the very beginning of May, but Waterloo can have it maybe 1 week earlier. So they will be able to see your score and then give you the admission. So that's the reason is I see many students, their first time go to Euclid at grade 12, or maybe they didn't do a good job before, right? But grade 12, they did a good job. So they do not really receive the admission letter until at the end of April, at the very beginning of May. That is because they already see your score internally, and then they will give you basically the admission. So that being said, is that we can try to, never give up. Do as much as you could for the Euclid, even though grade 12, you still have a very good bet in order to get your admission from Euclid. Okay? So let's continue. Student got a question is, so you mentioned you are a grader of Euclid. Is there any common small mistakes many students would like to make in the contest? Any tips on how we should avoid it? That's a very good question. And this is exactly what we're going to say for our entire 10 lectures. There are so many tricks I like to show you guys, so many common mistakes people keep making. So there are so many. I have a list of more than 50. So I'm going to be able to show you guys one by one. The entire lecture of our bootcamp is trying to teach you guys about that. All right. So yeah, that's pretty much all I like to say as a very start. So if all good, we can actually jump to our today's lecture, lecture number 1. We're going to talking about 2D geometry, especially focus on triangles, quadrilaterals, polygons, so on and so forth. All right, so let's get started. So our lecture, we never just directly jump to problems because there's so many problems. So on the contrary, this is like the structure how we organize our lecture. Our lecture always be organized into 3 categories. The first category is the concepts. So before each section, we like to give you guys an overall concepts summary, give you guys the most important concepts that you need to know in order to go to that part. And then second part, we're going to give you the important type of questions. You know, there's so many questions, right? We won't be able to cover them one by one. I have already summarized them or classified them into different categories. And for each category, I'm going to give you some summary. Okay, these are the very important, very popular questions you're expecting for the math competition. And number 3 will be real problems. So we're going to give you the classification, and then I'm going to give you the sample problem for each of this classification. So moving forward, you will be able to see, okay, this is my problem, and this is how I do such a problem. And most importantly, you will be able to find out, actually, there are so many similarities. So later in today's problem, you're going to be able to see that, you know, there are some shapes, you know, like 1 year they tested, another year they test it one more time. As long as you see such a shape, you should go for such a decision process. So everything will be what we call a conditional reaction. I want you guys to keep remember this as conditional reaction, because if everything you see it, you think about it from the very beginning, you have no time, right? We're going to have like 2.5 hours. But if you put everything just like a imprint as kind of a conditional reaction, you solve a problem, you have the answer right away. So this is going to be a very natural process. So this entire lecture, we're going to teach you all those kind of conditional reactions. If you remember them by heart, it's going to help you expedite your process. All right, so if all good, let's fly to our first part. Let's try to do some quick summary about the most important stuff for the 2D geometry, talking about the triangles, the quadrilaterals, the polygons, so on and so forth. The first one, this most important thing is the triangles inequality, right? As long as you got a triangle, you'll be able to find a inequality relationship between the 3 sizes, right? And this is actually crucial because sometimes when the question just gives you a triangle without giving you any special conditions, but the question asks you to solve an inequality or find out some range. So most important thing you can think about it is try to find out the intrinsic inequality of a triangle. In our case, is triangles inequality. And also there's another thing you can think about it. In a triangle, because in a triangle, we always have a theta value is between 0 to 180 degrees. So therefore, the sine value and the cosine value, you will be able to find out something, right? So the sine value could be what? Could be from 0 to 1, right? And the cosine value could be from -1 to +1. So that being said, you also have another range talking about the trigonometry. So there are 2 very important intrinsic inequalities in a triangle. Without giving you anything special, you will be able to write it out. Okay, that's our first thing. Second thing is everyone knows that the Pythagorean theorem. This is like so easy. You learned it in your elementary school. So for the Pythagorean theorem, most of the time, the question won't really give you a Pythagorean and then ask you to see, okay, what is the C under root A squared plus B squared? Alternatively, what's going to happen is that maybe the question just give you a triangle with 3 sizes. Sometimes they give you the 3 sizes. Sometimes you have to do the calculation about the 3 sizes. And then as long as you do the calculation, you should be able to realize, okay, these 3 sizes are actually a Pythagorean triple, aka they are the 3 sizes of a right triangle. So that being said, even though the question does not really give you a right angle, but you would be able to reversely, doing the reverse engineering, figuring out, okay, this is a right triangle by recognizing the Pythagorean triples. So actually there are 4 very important Pythagorean triples. I list them out. So they are very commonly tested, not only in Euclid, but also in the American math competitions. So try to get yourself more familiar with those numbers. As long as you see those numbers, your first reaction might be, okay, this might be a right triangle. So 90 degrees would be automatically created. There are a lot of interesting properties could be elaborated from there. Okay? So moving forward, let's go to the third part is the congruency. I think congruency is fairly easy, right? 2 triangles congruent to each other means they're exactly the same. You have different determination rules. You know, the 3 sizes, 2 sizes plus an angle, right? 2 angles plus a side, angle, side. And especially for the right triangles, you have one of the hypotenuse and one of the like the right leg, right? Like the leg, that's good enough. So, and also there's one thing I want you guys to remember, I think you guys already learned that in your day school, is SSA. This is not the correct way to identify 2 triangles that are congruent to each other. So what does it mean? It means that, let's say, if I have a side, I'm gonna use the color. Here, they're both 11. And I have an angle, which is 30 degrees. And I have another side. So 2 sides, and one side is the opposite angle, right? In that case, you can actually construct 2 triangles, right? So the big triangle, definitely they are congruent to each other, but there's another small triangle, the obtuse triangle, right? You find out, you know, this obtuse triangle, this is not actually congruent to the big one. So that being said, the SSA, this is not a correct way to determine 2 triangles that are congruent to each other. We're only going to focus the previous strategies, right? I think this is something so easy. We just want to take this opportunity to give you guys a quick summary. So in a nutshell, you can find out if we want to determine 2 triangles that are congruent to each other, at least, I'll say, at least, you need to have a side condition, right? You can have 3 side condition, you can have 2 sides condition, but at least you need to have 1 side condition. You can't only have angles. Well, as long as you go to similarity, these criteria can be a little bit loose. How to determine 2 triangles that are similar to each other? 2 angles. As long as you get 2 angles, it's good enough, right? So what about 2 sizes and this included angle, or 3 sizes? So that being said, in order to determine 2 triangles that are similar to each other, is actually more loose, right? Similar means they just look alike, but congruency means they must be exactly the same, right? So therefore, to determine 2 triangles that are similar to each other, as long as you have 2 angles, or you have some side and some angle, they're both working. So generally speaking, from math competitions perspective, the similarity is way more important than congruency. If you guys go to the American math competitions, you're going to find out most of these flowery, complicated theorems that are all elaborated from similarity. Well, congruency is kind of like limited. And actually, the case is the same for Euclid. They will focus way more on similarity rather than the congruency. Okay? So let's continue. Number 5, the law of sine and the cosine law. Trust me, these are actually 2 very important strategies, and Euclid and the American math competition just keep testing it from time to time. So for the sine law, it goes like this, right? A over sine A, B over sine B, C over sine C equals to 2R. So what is this 2R? This 2r is actually r is the radius of the circumcircle. Is it right? R is the radius of the circumcircle. So this is the sine law. And another law which is way more important, actually way more important than most of the other laws, is the cosine law. So cosine law, you know, there's a relationship between it, right? So why I say like cosine law is like so important, I'll give an example. Let's say, I want to say cosine A equals to B squared C squared minus A squared to BC, right? So cosine law is the special law that you can separate the angle relationship and the side relationship on the two sides. You see, on the left-hand side, you only have angle, right? And on the right-hand side, you only have side. So that being said, it's a special law. You can generate the angle condition simply from the side condition. What does it mean? It means that, let's say if I give you a problem, the problem only gives you some side, some random relationship between the sides. And also at the end of the day, the question asks you some angle related stuff. If you see that, this is going to be a conditional react. The question give you side, ask for angle, or give angle, ask for side, then you must use the cosine law. Because the cosine law is the only important law which find out the relationship between the side and the angle. This is very important. Trust me, they're going to test it from time to time. You're going to be able to see a lot of interesting problems. I elaborated from there. A student got a question, what does this R mean? R is the radius of the circumcircle of this triangle. You know, any triangle, you can put it into a circle, right? And this R is the radius of the circumcircle. We can provide more information regarding that. And there's a lot of fancy, interesting theorem based on this property. Okay. So moving forward, area of a triangle. This is actually a very important thing. If you do statistics for the Euclid, you can find out there are so many problems of Euclid. They're actually testing a lot of area-related stuff. They want to ask you how to determine the area of certain triangle, or how to determine, you know, the area portion, the relationship, so on and so forth. There's so many things. So how to determine the area of a triangle? This is actually very crucial. So let's try to spend maybe some paragraph, try to do a quick summary. So first thing first, how to determine the area? We learned that from our elementary school. You can use the bottom and you can use the height, right? 1/2 height times bottom, you'll be able to get your area. That's something so easy. And the second one is the famous Heron's formula, right? If I give you a triangle with A, B, C, 3 sizes, instead of like finding the height, then you will be able to directly using the Heron's formula, you know, to find out the A, which is under root S minus A, S minus Z, and S minus C, and then you will be able to find out the basically the area of this triangle, right? The Heron's formula, everyone knows that from your elementary school, I would say. So these are actually two very important stuff, okay? And actually, you know what? This property can be elaborated into a quadrilateral, okay? If I have a cyclic quadrilateral, cyclic, not random quadrilateral, cyclic quadrilateral. If I have A, B, C, D, 4 sizes, do you know how to determine the area of this quadrilateral? Do you know any special tricks how to determine the area of this quadrilateral? Just a quick question. I don't know if you guys ever know that or not. Do you guys heard about that? It's actually a very interesting property. Do you guys know that? Actually, you know what? You have something quite similar. You'll be able to determine the area of this. Yeah, somebody mentioned the extended Heron's formula. That's pretty good. Yeah, this is actually, if you have a cyclic, you'll be able to define S, which is A plus B plus C plus D divided by 2. And your area will be S minus A, S minus B, S minus C, S minus D. Quite similar for the Heron's formula, right? Because any triangle can be inserted into a circle, but not all the quadrilaterals can be inserted. So my pre-assumption is this is like a cyclic quadrilateral. Okay, this is also something quite comparable. It's an interesting property, right? If you know a cyclic quadrilateral, how do you determine the area? No need to waste your time. You can just directly jump to the extended version or the generic version of the Heron's formula. Okay, so if all good, let's continue. Actually, there's another very important thing for you to determine the area is the shoelace theorem, right? This is more like from a coordinate geometry's perspective. As long as you got a coordinate geometry, you have like 1, 2, 3, the coordinate of the 3 points. So how can you determine the area of this triangle included by these 3 points? There's no need for you to determine, the D value for here, another D value for here, another D value for here. No, that's too much. You can directly using the shoelace theorem to determine the area of this given triangle. Okay, this is what we talk about in our regular lectures, right? So we have the regular lectures give you more kind of like a inside explanations, but this is the bootcamp lectures. We're just going to be more jumping, right? We have like kind of like, I assume that you guys already have some background knowledge before come to the bootcamp lectures. And actually this can be more generic as long as you have like a convex polygon, right? And you have the coordinate about each of the vertex, then you will be able to find out this is like the generic form how to determine the area of a convex polygon. This is also something very interesting. I don't think you have to remember it because this is like a kind of like a big formula, but you need to understand, right? As long as in the coordinate geometry world, we can always easily determine the area of a given polygon. Okay. Number 7. The most important thing is the Stewart. Stewart is actually a very important theorem, and I want you guys to remember. So what is like a Stewart? Stewart theorem actually reveals an intrinsic property of any triangle. Let's say I got a triangle. This is my triangle. So this triangle, you have like so many sizes, right? So let's say, I'm going to say this is like your side C, D, B, M, N. And let's say this is A, okay? As long as you have a triangle, you want to find a point on one of the sides, make a connection, you will automatically have 6 segments, okay? So trust me, there's an intrinsic relationship between these 6 segments. What is that? M times A times N plus D times A times D equals to B times N, M times B, plus C times N times C. It means that there's nothing really special for the triangle. Any kind of triangle, you will automatically have such a relationship. So that being said means what? As long as you know 5 segments, you'll be able to calculate the 6th one, right? Because the 6th one has a relationship. You know 5, you automatically know the last one. Okay, but how can you remember this? This looks like a very big formula. You can actually remember this like this. You can say a man and his dad put a bomb in the sink. This is a shortcut way for you to remember this. A man and his dad put a bomb in the sink. That's the way how you remember it. You can just keep saying that. A man and the dad put a bomb in the sink. A man and his dad put a bomb in the sink. You can keep saying that. Of course, don't say that when you cross the border. But I'm just trying to say that you can just try to say that like a bit more times, then you'll be able to remember this. Okay, this is a very good way for you to remember the Stewart theorem. And there are two more theorems. You do not see them very often in Euclid, at least for now, but I think it's always good for you to remember it, at least to expand your horizon. So one is the Menelaus, the other one is the CVAR. These are very important for AMC and AIME, but for Euclid, you can just have a look at it. So the first one is like, as long as you're a triangle, you got a triangle ABC, okay? And you have a transversal line. So this transversal line cut ABC triangle's two sides and extend on the other side is extension. So you have PB, okay? You have like PB over CP times QC over QA times AR over RB. So you basically do a transverse between the three sides of the triangle. You basically multiply them together and the product is going to be equal to 0. Again, this is an intrinsic property for the triangle. We have nothing really special talking about a triangle. Any triangle, you have this property. In our regular lectures, we actually give you guys so many problems, so many examples, how to use the Menelaus theorem. So in our bootcamp lectures, we just give you the example, give you basically the theorem. You can reference to our previous lectures. The other one is the CVAR. CVAR is also something so generic. As long as you got a triangle, you find a dynamic point in the middle, and then make extension, make extension, make extension, then you'll be able to have BD over DC, CE over EA, AF over FB, multiply them together equals to 1. So these two theorems, they're both elaborate from the similarity. So that's, like I said, similarity is way more important than the congruency, and using them can reveal the intrinsic property of your triangles. Okay? So generally speaking, these are the most important properties that you need to know in order to go to the Euclid math competition, talking about the 2D geometry, the triangle, the quadrilateral, the polygon side. So this is actually our section number 1, talking about the concepts. Okay, so second part is, let's try to do some summary. What are the classic problems you're looking at when you're dealing with the Euclid-related problems in the 2D geometry parts? So generally speaking, I would say if in the Euclid, you're looking at 3 major important types of problem, talking about this part. The first part is talking about area. So trust me, area is actually a very important topic in Euclid. They may not really ask you to do area, but they might ask you to do something, or maybe use the area, try to prove something, or maybe during the process, you can use the area to help to expedite your calculation process. So area is kind of like a medium or like a liaison you need to use in order to solve the problem. So talking about the area part, actually you're looking at 3 major important strategies. The first one is rotation. We're going to give you guys more details whenever we go to the real problem. Rotation is kind of like, it actually speaks for itself, rotation, right? Rotate the shape. Using some rotation, and then try to find out some congruency and transfer the property from one side to the other. So later, we're going to give you problems, you understand what I'm talking about. So rotation is one of a very important strategy in Euclid. Second way, try to determine the area is compensation. Compensation means that whenever the question gives you a weird shape, you have no idea how to do it, but you want to maybe add something or subtract something, just try to compensate the original shape. Let's say if the shape is something like here, maybe you can add something here to make it as from a weird shape into a triangle. Or if you have a shape like this, maybe you just need to cut it, only half of it, do some algebra manipulation, add something, subtract something, and then you got a new shape, and taking from there, solve the problem. This is what we call a compensation method. And the last one is partition method. Partition is more like sliding, right? You're going to cut them into different parts and then try to see how you can reorganize all those parts together and then do the problem. So these are the 3 very important strategies that when you're dealing with the area method, and I'm going to give you more examples in the later part. So this is number 1, talking about the area. Number 2 is you're going to try to use some simple theorems. Try to solve the problem. The simple theorems could be something like the Pythagorean theorem or like the cosine law. You know, all those kind of theorems, they can really help you to expedite your calculations significantly. It's kind of, you can use it, or you can use a long way, a very complicated standard way to solve it. But using some cosine law, using some Pythagorean is going to really help you to expedite your calculation process. We're going to give you some examples and you understand where I come from. And number 3 is, you know, similar triangles, important property. You know, similar triangles, the most important property is what? So the sides are proportional to each other, or like the angles are the same, right? One is side, one is angle. But trust me, there's another very important property that comes from the similarity, is that as long as 2 shapes are similar to each other, the area ratio would be the similarity ratios for a fixed square. Is that right? The 2 shapes that are similar to each other, not necessarily triangle. It could be a quadrilateral, could be a circle, could be whatever. The area ratio of 2 similar shapes will be the similarity ratios for a fixed square, right? This is actually a very important property. You're going to use it very often from time to time. They're really going to help you to expedite your calculation significantly. All right, so this is our second category, talking about the classical problems. So this is only like from strategies perspective. Now let's go to the third part. Let me give you the real problem for each of this category and show you guys how you're going to think, how you're going to solve all those problems. So let's go to the third category, is real problems. Okay, so let's go to the first one, right? Area method. I mentioned there are 3 strategies, right? Let's go to the first one, the rotation. Let's go for a real problem from Euclid. There you go. This is a problem that comes from, so the year is 2016. This is problem from 2016. Euclid, question number 9, B part. Okay, let's have a quick look at it. So the problem says, in the diagram, ABCD is a square. Okay, I'm going to highlight. Okay, you're going to learn from me. As long as you read the problem, highlight the most important part. Okay, ABCD is a square. Points E and F are chosen on the AC so that EDF, this guy. Okay, I'm going to use the color. EDF, this guy is 45 degrees. Okay, if AE is X, EF is Y, and FC is Z, try to prove that Y squared equals to X squared plus Z squared. Okay. Who can tell me, just basically by reading the problem all the way to here, the question asks you to prove Y squared equals to X squared plus Z squared. So what should you use? What kind of technology? So generally speaking, what can you do in order to make it in such a way? When you're reading the problem, you're probably going to think about what is the solution approach, even though you have no idea what to do, but they're kind of like looking like what? Yeah, I see somebody, Andrew has, and Michelle has the correct answer. Yes, you're pretty much going to use the Pythagorean theorem, right? this really looks like the Pythagorean theorem, kind of like two sides, perfect square, and then generate another square. Well, if you want to use the Pythagorean theorem, of course, you want to put it into a right triangle, right? This is what you're going to do. But for now, your x, your y, your z, they're not even in the triangle, right? They're basically in the same line. So this is not going to happen, right? X, y, z, they're actually in a line. No, you have to put it into a right triangle in order to make it happen. I think these are something quite common sense, right? Even though I have no idea how to do the problem, but these are actually the conditional reaction. You see this, you realize you might have to use the Pythagorean, but try to use the Pythagorean, you need to find a right triangle. And I need to put like the three sizes into the right triangle. Y will be the hypotenuse, X and Z, they will be the two sizes. So that's gonna be the solution process. But at this moment, you do not really have anything, right? So the $1,000,000 question is, how can I make sure the X, Y, Z, they need to be closer to each other, right? They need to be in the same triangle, and then I can make sure everything can proceed. So in this part, the rotation methodology comes in. What does rotation mean? Rotation means you rotate, right? You basically turn something from one side to the other, and then to make it, the same side, the transfer element, so on and so forth. And how can I do the rotation? So trust me, this is a very common strategy. You want to move X and Y as close to each other as possible, right? Maybe in this case, I'm going to move the X. X is here, right? How can I move X? I cannot just move X itself. I need to move. A rotation means I'm trying to rotate a shape. So I'm going to rotate your triangle ADE. How can I do the rotation? I'm just going to rotate 90 degrees to here. I'm going to highlight it here. This is my original triangle, ADE. I rotated 90 degrees to here. I'm going to give a denotation for this vertex, maybe M. Okay. I'm going to rotate triangle ADE to triangle DMC. Because you do a rotation, obviously these two red triangles will be congruent to each other, right? You just do a rotation, nothing changed. Okay, as long as you did a rotation, trust me, there will be some magic happening here. Let's have a quick look. So first of all, if you do the rotation, of course, you're going to have these two sizes are the same. You just rotate it, right? So nothing changes. So this guy goes to this guy. Okay. And besides that, what else we can do? Let's have a quick look at it. Because you do the rotation, so this angle will be the same as this angle, right? These two dot angles are the same. Okay. Previously, when you saw the original square ABCD, I'm going to say something. The blue dot and the yellow dot, adding them together equals to what? 45 degrees. Is that right? Yeah, because the total angle ADC is 90 degrees, and you're telling me the one in the middle, this is 45. So the remaining two will be 45 degrees in total. So I will say that angle ADE plus angle FDC equals to 45 degrees, right? So this is the blue one. This is the yellow one. Now, after your rotation, you know that angle ADE is the same as angle CDM, right? This is the blue dot. This is the blue dot as well. So therefore, you do a quick replacement. FDC plus CDM equals to 45 degrees as well. FDC is my yellow one. CDM is my blue one. Oh, you're talking me this guy is also equals to 45 degrees. Okay. If that's the case, okay, let me try to have a look at it in these two triangles. I'm going to do a connection. Go here. Let's focus on these two triangles. One triangle is this green one here. The other triangle is my green one here. Let's try to see what's going to happen here, okay? So for these two triangles, I have already know that DE is the same as DM. DE is the blue one, DM is the blue one. And also I know that these two guys, angle FDM equals to 45 degrees. This is equal to EDF, right? These two red angles are both 45 degrees. And what's that? They shared a DF side. Shared. So that means what? Two triangles, two sizes, and the included angles are the same. So therefore, these two green triangles would be congruent to each other. Is that right? So therefore, triangle EFD and triangle MFD, they are congruent to each other. Is it right? Oh, if they are congruent to each other, you see, if this is y as well. Okay. Why I'm doing this? What's the point? Why I'm doing this? I'm trying to transfer x, y, z to each other as close as possible, and hopefully I can build up a right triangle and do the Pythagorean thing, right? Now, because you did a rotation, your x has already been transferred here as an x. And then you find out these two green triangles, they are congruent to each other. So your y, if I change a different color, your y has been transferred here as y as well. Ah, your z is here never changed. So now x, y, z, they all go to a same triangle, the black triangle here. Is that right? Oh, if I can do some quick calculation, if I can find out the shape of this black triangle is indeed a right triangle, then my work is done. Then who can tell me, is it very challenging to prove that this black triangle is a right triangle or not? Who can tell me? How can I prove this black triangle is a right triangle or not? Yeah, I see pretty much everyone has the answer right away. This is an easy peasy problem because if I zoom here, definitely this is 45 degrees, right? It's half of the, it's kind of like diagonal. And also my angle here is the same as the angle here because these two red triangles are actually congruent to each other. And this is 45 degrees. For sure, this is also 45 degrees. So therefore, you can just basically say, obviously, angle FCM equals to 45 plus 45 equals to 90 degrees. So therefore, using Pythagorean theorem, you can find y squared equals to x squared plus z squared, QED. You see, that's the solution process. It's fairly easy, right? Nothing complicated. You just basically do a rotation, transfer x from the upper one to the lower one, and then do all your magic within this little triangle, and then your work is done. Is that right? So therefore, trust me, here comes like a very important common sense. As long as the question give you a square or an equilateral triangle, like whatever, they give you something fixed in the middle, 30 degrees, 45 degrees, like whatever, I don't care. And then you see E and F, right? So these two parts are actually moving here, moving there, but the angle is always fixed. In that case, most likely, you're going to use the rotation strategy to rotate one of the triangle from here to here. This is actually a very standard way how to do problem. As long as you have a fixed angle in a fixed angle, right? This is a fixed angle. This is also a fixed angle. You see a fixed angle. I'm going to give you the quick conditional reaction. You see fixed angle within another fixed angle. Most likely, you can use the rotation. This is like a standard technology how to solve the problem. Okay, we use one problem. We try to remember what the question is trying to test us. You know what? If you're good, let's go for another example. Another example from Euclid, you're going to find out that this problem is exactly the same as the first problem that we just talked about. Give you the second problem. That's the first one. Okay, I'm going to give you another one. Number one. There you go. Okay. This is another problem. We're also going to use the rotation. This is a problem from 2009. 2009 Euclid, question number 9, B part. Okay, trust me, this problem is using exactly the same strategy. So the problem says you have a PQRS is a square with the side length equals to 4, okay? And point T and Q, they're on the two sizes, QR and RS respectively, and that UPT equals to 45 degrees. You see, this is exactly what we said. A fixed angle within another fixed angle. With all those information, the question asks you, what is the maximum possible parameter of URT? Okay? So you have a square, you have a fixed angle, 45 degrees, and then with all those information, the question asks you, what is the maximum parameter of triangle URT or RUT? How can we do such a problem? How can we do such a problem? Well, this is pretty understandable, right? You want to find out the maximum value about what? TU plus UR plus RT, right? That's basically what is the maximum value for this. Okay, now they're good. They're within the same triangle, which is good. But you need to find out some relationship in order to find out the maximum, like the minimum, so on, so forth, right? How can we find out the value? I don't know. But according to our conditional react, as long as you see a fixed angle within another fixed angle, we're pretty much going to do some kind of like rotation to make sure it works. So this is like conditional react, right? As long as you have this conditional react, you don't have to think from the very beginning. Let's just try to follow your heart, follow your conditional react. You might be able to expedite your calculation process. So there are two triangles, you can do rotation, right? So I'm going to do this one. This is exactly the same as we did for the last problem, right? You see? There's a huge similarity talking about the Euclid problems. So now I'm going to do a rotation. I'm going to do like this. I'm going to rotate this guy to here. Right? I'm going to say this is V. So obviously, these two guys will be congruent to each other, right? So see, triangle R, triangle PSU will be congruent to triangle PQV. Okay? And the same thing, as long as you see the congruency, blah, 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 then you'll be able, this is exactly the same thing, right? You'll be able to say this angle is the same as this angle. Previously, within the square, the black plus the yellow equals to 45 degrees. Now, you're going to be able to see this guy equals to 45. You see? This is like a given, right? These two problems are exactly the same. So what you can do, you just copy paste whatever you learned from the previous problem. You'll be able to find what? This guy is the same as this guy because you did the rotation, right? And 45 degrees is here, 45 degrees is here, plus they're sharing the same side. You see, they're exactly the same. So therefore, what? This green triangle would be the same as this green triangle, right? They're congruent to each other, right? You see? Exactly the same. See, this is Euclid. As long as you know one, you know the other, right? You have to really learn, have to summarize and learn the similarity. So that being said, I'm going to write a very top important thing. So I will say, obviously, triangle PUT will be congruent to triangle PVT. All the reasoning we have already talked about here, right? Exactly the reasoning. So if these two triangles are congruent to each other, what do you want? The most important thing is that you want to say this side. I'm going to use the color black here. This side will be the same as this side. Is that right? Ah, because you're trying to ask me what is the maximum or the minimum, like whatever, for TU, RU, RT. For this moment, TU is already here. Right? TU has been transferred to here. Okay, so let's try to do a quick calculation. You wanted me to know what is TU plus RU plus RT, right? So that one is going to be UR plus RT plus TV, right? Because your TU has been transferred into TV. Okay, so let's continue. For my, I want to find a maximum one. Let's try to see. UR, I don't know what to say. You are just here. So what about my RT? My RT is here, nothing to be special, RT. And my TV, okay, my TV can be broken into two parts. Okay, VQ and QT, right? My TV can be put into VQ and QT. TQ and QV, right? And this guy, RT, TQ. I'm going to put them together as RQ. RQ is one of the sidelines of my square, right? So this is UR. This is going to change into RQ. And QV. QV, I'm going to change the color. QV is here. QV is actually the same as SU, right? Because they are actually congruent to each other, right? So this is going to give you the SU. So let's try to see. UR is here, SU is here, and RQ is here. Oh my God, that actually means what? SR plus RQ, right? Because these two guys, adding them together equals to one side of the square, SR. So this is another side of square, RQ. So SR plus RQ is actually 4 times 2 equals to 8. Oh, actually, the perimeter of this triangle RUQ, there's nothing really the biggest or the smallest. This is going to be a constant, right? So the parameter, there's no maximum or minimum. This is going to be a constant. So actually equals to twice of the side length of the square. You see, the process is fairly understandable, right? There's nothing really complicated, nothing really special. As long as you remember, you see a fixed angle within another fixed angle, then most likely you can use the rotation technology, try to expedite your calculation process. So 2 problems, very similar to each other. They're like 7 years apart, right? But they're using exactly the strategy that you need to remember. Okay, I think 2 examples is good enough. Try to remember rotation plus the congruency is going to be very helpful for you to do the calculation. Okay, so far so good. This is our first technology using the rotation. Now let's go to our second technology using the compensation. So let's go for a problem. This is a problem that comes from, see the year, 2012 Euclid, question number 9, B part. So let's have a look at it. How are we going to do such a problem? So this problem says what? Says in a diagram, you have a quadrilateral ABCD and has the point M and N on AB and CD respectively, with AM over AB equals to NC over DC. Let's have a look. AM over AB and C over DC. Okay, it's pretty weird. I don't even know what it is. Okay, but anyway, I'll just leave it here. I don't even know what to do. I'll just continue. Line segment AN DM, they intersect at P, while BN CM intersect at Q. Prove that the area, I'm going to remove this, the area of triangle of the quadrilateral PMQN, oh, this is a very weird shape in middle of nowhere, tilt there. Okay, so this weird shape equals to the sum of the area of triangle APD, okay, and BQC. Oh my God. These are 3 weird shapes, 2 triangles flying on the 2 sizes, and a weird tilt quadrilateral in the middle. So the question said, want to show PMQN's area equals to triangle APD's area plus triangle BQC's area. Well, how can I do this, right? There are 3 weird shapes. I can't find the height. I can't find the bottom. I just cannot do anything. So here, I want to teach you guys a conditional reaction. As long as you find any weird shape or some flying shape, some tilt shape, right? As long as you find this weird shape, most likely you're going to use the compensation method. AKA, you need to try to add something or subtract something, try to make it happen. Add something or subtract something, try to do some further analysis. Okay, because you have no idea how to do such a weird thing, right? This weird shape, I have no idea what to do. But let's try to see if I can do some algebra manipulation. Hopefully, I can make it work. Well, you know, But what I need to do, right? What I need to add, what I need to compensate in order to make it work. You see this weird shape here. The blue one in the middle, the two red ones on the two sides, they're actually in the middle of nowhere. But I'm going to try to do something like this. Think about these two things. One is a triangle P and D. And the other one is triangle Q and C. Let's have a look at it. How are you going to do with such a thing? So want to show this guy. So I really have no idea how to do this. But if I can prove P, M, Q, N, add triangle, these two green ones, P, D, N, triangle Q and C equals to APD BQC plus PDN QNC. So what I'm trying to say is that, okay, I'm going to add the same thing on the two sides of this equation, right? So if I can prove this, I remove the same thing on the two sides, it'll be exactly the same. But trust me, as long as you do this, the work will be changed significantly. This is what? The blue one, okay, look at here. The blue one plus the two green one. This is going to be your triangle MDC, right? This is your triangle MDC. Want to show, right? And the green one, the big green one plus the small red one will be your triangle ADN, right? The small one, APD on the left, plus the big green one will be your triangle ADN. And the relatively bigger red one plus the green one will be your triangle BNC. Oh, now what you are trying to do is that you want to find out the triangle MDC's area equals to triangle ADN's area plus your triangle NCD's area. This is something like at least more appealing, right? Because these are like some regular triangles. You have the bottom, you have the side, so on and so forth. Now what can I do? These are the big triangles. I don't think you can do too much. You just go for the definition. Let's try to find out the height of them. Hopefully, I can solve the problem. Here, 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 right? This is the big one. I say this is M. Okay. This is A. This is B, right? I find the three heights. There's nothing too much I can do. I just go for the height, right? So what I need to do is that, let me try to see what's going to happen, is for my big triangle, MDC. MDC is the big triangle, MDC. MDC, you know, is here. I'm going to use the color. MDC. So this triangle is going to be the area, it's going to be 1/2 M times DC, right? So want to show 1/2 M times DC. So DC, I'm going to give a name. Maybe I'll say DC equals to X. Okay, just want to make my life easier. DC is X. So this is X. Equals to ADN. ADN is here. ADN. ADN is actually my bottom, which is the DN, and my height is A, right? But here, let me try to make my life easier. I'm going to say this is, I'm going to give a name. This is TX. This is 1/TX. Okay? Because the total is X, right? I'll say that DN is TX. The NC is 1 minus TX. So this is going to be 1/2 A times TX. And B and C. B and C is the last one. I'm going to use the color blue. B and C. B and C is actually this guy. It's going to be 1 over Tx times the height B. 1 over 2, right? 1 over 2 Tx times B. Okay, so that being said, you just have to prove this. So there are a lot of x here. I'm going to remove this. So therefore, you just want to show m equals to t times a, 1 minus t times b, because the x could be eliminated, right? How can I prove m equals to t times a plus 1 over t and times b? A student got a question, what is t? T is actually a parameter I just said. I let dn equals to tx. I just say t. There's nothing about it. It's a parameter. You really have no idea what's the value of the t. So if this is tx, this is going to be 1 minus tx, right? Because the total dc is x, which makes sense, right? All right. If that's the thing, so the $1 million question is, how can I prove this guy? M equals to t times a plus 1 minus t times b. Well, in order to do that, I have to go back to the original shape, right? This is basically what I'm looking at. I'm trying to do a quick extraction. I'm going to extract it out. Okay, just give me 1 sec. I'm going to extract it out. So this is going to be my trapezoid here, right? This is A, this is B, right? What else? This is the M, right? This is E, this is F, this is N. You're telling me this is A, this is B, this is M, right? According to this, A, B, M, right? I'm actually extracting out this trapezoid. You have this. Okay, so basically within this trapezoid, you need to prove such a relationship. Okay, how can you do that? So this part is exactly what we mentioned in our regular lecture. As long as you see a trapezoid, what are you going to do? Always, this is a conditional reaction, okay? In trapezoid, what are you going to do? Always, you want to make a perpendicular line from the top to the bottom. From the top to the bottom. So let's say this is R. So within this triangle, you can automatically say what? MR over, let's say this is S, SB will be equals to AM over AB. Is that right? MR over SB will be equals to AM over AB. This is understandable, right? So what is MR over SB? MR is actually what? M minus A, right? This is M, this is A, MR will M minus A. What about SB? B minus A, right? So these two parts, if I do a ratio, will be equals to AM over AB. AM over AB. Is it like a deja vu? Something's familiar? Yes. AM over AB is actually what? NC over DC, right? This is NC over DC. NC over DC is actually what? NC over DC is NC is here, DC is here. NC is 1 minus T times X. DC is X, right? 1 minus T times X, and DC is X. So therefore, you have M, I'm going to use the color black, M minus A, B minus A equals to 1 over T. Look, so easy, right? n minus a, b minus a equals to 1 over t. Trust me, if you do a very quick, simple simplification, this guy is going to generate m equals to t minus a, 1 minus t, b. This is exactly what you need to prove here. So, QED. That's it. This is also question number 9. This is not a super easy problem, but generally speaking, you're using the compensation method. You're compensate, right? From the weird shape, adding something into a big shape. The big shape is actually a triangle, and taking from there, you will be able to solve the problem. You see, the entire thinking process is fairly understandable. You're not asking something too complicated. So far, so good? Okay, so this is actually our compensation method. Compensation always asks you to what? Add something, remove something, subtraction, sum, then to generate some easy shape. And taking from there, you'll be able to solve the problem. So far, so good? This is our second part, using the compensation method. If all good, let's go to our third part, using the partition method. And this is like a difficult one. A partition method is not easy, but I really like to show you guys some difficult problems, and you'll be able to see the beauty of the Euclid math competition. Partition method. So let's go for the partition method. Let's go for a difficult problem. This is a problem that comes from, yeah, this is a difficult problem. But trust me, you understand what I'm talking about. This is something understandable as well. And also, I'm going to show you my solution is way more easier than the official solution of Euclid. Later, I'm going to show you the official solution is crazy. You don't even know what it's talking about. So this is a problem from 2013. Euclid, question number 9. A and B, 2 parts. Still remember, if you have 2 parts, then whatever you get from the first part might be useful for the second part. Let's go for the first part. The first part says what? You have a square WXYZ has a side length 6. I'm going to highlight it here. So this is drawn as shown completely inside a larger square, EFGH has a side length 10. So that the 2 squares do not touch each other, and WX is parallel to EF. Okay, so these these 2 squares, they're parallel to each other. Prove that the sum of the area of the trapezoid EFWX, this guy, the trapezoid, and the trapezoid GHZY, this guy. You have 2 trapezoid, right? So the question says the area sum of these 2 trapezoid does not depend on the position of the WXYZ inside EFGH. So basically, the 2 red ones, adding them together is a fixed value. It has nothing to do with the position of XY, ZY, XY, like WZ. Well, this problem is always the A part. Like I said, A part is always easy. You don't really have to send too much effort. You'll be able to find it very quick. So you just do the calculation, right? The question says what? You want to find out the area sum of this 2 trapezoid. So the first trapezoid, EFXW, is going to be what? 1 over 2 top plus bottom plus height. Height, I don't know. I'll say height is H1. Right? The second was what? YZGH, 1 over 2, top plus bottom plus H2. This is 6, this is 10, right? This is H2. So adding them together, the sum will be 1 over 2, 16, times h1 plus h2. What is h1 plus h2? What is that? Who can tell me? What is h1 plus h2? And this is easy, right? h1 plus h2 is basically the difference between the large square side and the small square side, right? So it is actually 1 over 2, 16, 10 minus 6. So the value is 36. That's it. Easy peasy. A part is always given. Do not waste any time. Do not hesitate. You can definitely do the A part. Okay, let's go to the B part. B part might be a little bit challenging. So the B part is that a larger square ABCD is shown with a second smaller square completely inside it so that the square do not touch. The line segment, they're all given. Diving the region into basically 4 non-overlapping convex quadrilateral. If the side of PQRS are not parallel to ABCD, well, previously the problem is parallel, right? But now it becomes acute, not parallel. Okay, so prove that the sum of the area APSD is here. I'm going to use the color maybe red. APSD, okay, this red one. And BCRQ. Okay. So these two red weird quadrilaterals, area sum equals to the sum of area ABQP. ABQP, okay. And SDCR. Oh, you want to prove these 2 red ones, adding those 2 blue ones. I mean, the 2 red ones adding them together is the same as the 2 blue ones adding them together. Okay. This is something not quite same, but something comparable, right? Well, the only difference is previously you have a parallel shape, but now you have 2 not parallel shape, right? The question says very clear, this is not parallel to each other. Well, how can I do such a problem? How can I do such a problem? Like I keep saying, most likely, whatever you do for the first problem must be transferable to the second problem, right? Otherwise, they won't bother asking you for the first problem. But how can I create a parallel shape based on the first problem? The second problem is not parallel, but how can I create something parallel to make it happen? This is a little bit challenging for this problem because I really have to use whatever I did for the first part, no matter what, right? By hook or by crook. So I just have to apply it for the second one, but the second one looks like I just can't use it, right? You know what? If I can't use it, I just have to use it. So what can I do? I'm just gonna do something like this. It's a little bit crazy, but I'm just gonna generate the shape that looks like the first one. I'm just gonna do some auxiliary lines to make sure this is exactly what I get from the previous one. You see, I add a lot of auxiliary lines. Now I'm kind of like falsely generate a shape, which is quite like the first one. Then I would be able to use the first one to get all the properties to get my second one. Is that right? And so that being said, all my shapes, my blue one, my red one, will be cut into small pieces. And this is the partition, the sliding, right? This is our method, partition. I need to cut my blue one into small pieces. Hopefully the small pieces, adding them together or subtraction or like whatever, will make sure they are the same. Talking about the calculation. I'm cutting them. Okay, so how can I do the cutting? I'm going to give you a more kind of like nicer shape. Okay, this is the nicer shape after I do the cut. So obviously the question, so what I need to do, I need to find out, right, in this new shape, the blue plus blue equals to red plus red. So let's try to have some quick calculations before we move forward, right? So obviously, whenever I see such a shape, oh, this is a little bit crazy, but no panic. This crazy shape, at least see something like this. Can you agree with me or not? These little red triangles on the four sides, they are all congruent to each other and have the same size. Does it make sense? So you have a triangle, you have a square inserted into another square. I'm going to say something. Have a square and then another square inserted here. So definitely all those little ones, they will be all congruent to each other. Does it make sense? I think this is easy peasy stuff, right? So we'll say, obviously, you have E equals to F equals to G equals to H, talking about all those four little right triangles. This is quite understandable. Second, from A part, we just know, right? The two red, adding them together will be the same as the two white adding them together because they're both independent for the position. So that being said, actually means what? If I want to do quick thing is, this is my blue one. I'm actually copy like the first question number one. This is my first blue one, my second blue one. So this guy plus this guy will be the same as this guy. Green one. One of the green one. This is another green one, right? This is what I know from question number one. Those two guys, adding them together, are basically the same. I'm gonna give you, just give me one sec. I'm gonna make a nice graph that you know what I'm talking about. Okay, so basically I know from A part, the blue plus the blue equals to the green plus the green, right? So what is the blue? A plus R. The next blue is C plus N equals to B plus M, D plus S. Is it right? This is understandable, right? But what you have to prove, is actually the tilt shape, right? Is this guy, the tilt shape. I'm just gonna write it one. Right? So what do you have to prove? We say want to show. What you have to prove is AB QP CDSR BCRQ ABQP. I just basically highlight one, but you know the other three, right? This is what you have to prove from the original question's perspective. So what does it mean? I'm just gonna give more, I'm gonna break it down, right? ABQP. ABQP will be what? A plus E plus S. This is ABQP, right? So I'm just gonna highlight it. A plus S plus E. You can do the same thing for all the others. C plus G plus M. B plus F plus R. D plus H plus N. Okay, this is what you want to show. Again, I keep saying this. This is what you know, right? The question already find out the three red, small, slim right triangles, they're the same. And this is also what you know. This is what you get from question number 1. This is two parts that you know. And this is the part that you do not know. So there's a gap between whatever you know and whatever you do not know, right? You need to bridge the gap, right? Do you guys follow me? So you know this. You know this. But you do not know this. You need to use the two black ones to generate the red ones. That's it. Right? How can I use the two black ones to generate the red ones? This is the $1 million question. Actually, in this part, the Euclid official solution is super complicated, but I'm just going to simplify it into one sentence, one line, and then that's it. Look at that. Because, I'm just going to say, because you have A plus R, C plus N equals to B plus M, D plus S. This is here. This is an equation, right? Within this equation, if you want to, again, make sure the equations are the same, and then you want to generate something you do not know, something just like E, something, see, you have M here. I'm going to use the color maybe red. You have M here. You have S here, right? You have N here. I don't really have anything in my following expression. I just blindly plus M plus S minus R plus N on the left. And then M plus S minus R plus N on the right. This is good, right? I just add the same thing on the two sides of my equation. Of course, my equation still holds, right? You know what? Trust me. As long as you do some quick rearrangement, this is going to generate A plus S plus E, C plus G plus M. This is going to generate B plus F plus R, D plus H plus N. This is exactly what you want to prove. QED. Look, that's it. So easy. You just use whatever you know, the first one, whatever you know, the second one, and then add something to the left, add something to the right, same thing, and then you automatically generate whatever the question asks you to prove. That's it. So easy. You get whatever you need. So easy. So far, so good? This is like so easy stuff. Trust me, if you check the official solution from Euclid, oh my God, this is like a nightmare. So I'm going to show you how they solve the problem. So I don't think I need to show you, but you basically see how they solve the problem. They use a very, very complicated, crazy way to solve it. And like I said, you won't be able to even understand. They have some cosine, sine, cosine. I don't know what they're trying to do. So just like I said, you do this, you do not even have the time to write it down, but not to say you can think about it. They use the weird sine, cosine thing here and there to do a lot of calculation. You see here, this kind of weird things. I don't even know what I'm talking about. So trust me, using my solution is a lot more straightforward. You can solve the problem just in a couple of lines. So in my entire lecture, I'm going to be teaching you guys how to use the easy way, try to solve the problem. Do not use the official way. This is crazy. And in our crash course lecture is every problem, I'm going to show you an easy way, try to solve it. Much easier compared with the crazy official solution from Euclid. All right, so this is our first category. So we're talking about the area method. I know we're running out of time. I'm always running out of time for our lecture number 1 because there's so many things to talk about. But if you like to bear with me, we can continue the lecture like a little bit. If you're busy, you're good to go, okay? So basically, that's our first category, talking about the area. And from the second category, from the second one, we can try to talk something about how to use some simple theorems, try to solve the problem. Some simple theorems to solve the problem. So I'm going to give you a problem that comes from, second one is going to be here. I'm going to talk something about the latest problem, like 2023, our last year problem, Euclid question number 8, A part. Okay, question number 8, A part. So the problem says a triangle ABC is right angled at B. And I'm going to give you the side like this. This is B, this is A, this is C. And you have AB equals to n plus 1, and AC, n plus 1, n plus 4, where n is a positive integer. As long as you say this, trust me, conditional react. Something does not have to be a positive integer, but I give you a positive integer, there must be some number theory related to discussion here. Could be as easy as factorization, as difficult as something else, but you know, always you're gonna see something in the number theory related discussion. So the question says, determine the number of positive integers lesser than 100,000 for which the length of BC is also an integer. This problem is a very direct problem using the Pythagorean theorem, right? Because you're trying to determine the value of BC. BC can be easily derived using Pythagorean. So BC will be what? Or BC squared will be AC squared minus AB squared, right? This is something quite easy. Using Pythagorean, you use it right away. So you just have to plug in the value, right? N plus 1, n plus 4, perfect square minus n plus 1, perfect square. You just do a quick simplification. It's going to be n plus 1 squared times 4, 2n plus 4. This guy, if you want a b to be an integer, so that b inside means what? Means this guy must be a perfect square number, right? So you take under root, so BC could be an integer. Otherwise, there will be irrational numbers, right? So how can I make sure this is integer? This is so easy. These two guys is 4 times n plus 1 squared. This is already a perfect square number. Then you just have to make sure this guy, 2n plus 4, is a perfect square number, right? 2n plus 4 is a perfect square number. How can I say this is a perfect square number? I think this is something very easy. You can do a quick calculation. Why? Because n is lesser than 100,000, right? So therefore, 2n plus 4 will be between 6 to 200,004, right? So let's do a quick calculation. So therefore, if you want to find out a perfect square number, the smallest perfect square number greater than 4, that will be greater than 6. That will be what? That will be, I'll say, right? If you want to take the even one, right? Oh, sure, this is going to be even because 2n plus 4 must be even, right? So the smallest even perfect square number greater or equals to 4 is going to be 4 square, which is 16. Does it make sense? So the first candidate is going to be 4 square, which is 16. All the way to 0.0004. If you do a quick calculation, you find out this is very close to 446 square. So this is slightly lesser than 2.00004. These are, because Euclid, you can use the calculator, right? The AMC does not allow you to do the calculator, but Euclid you can. So it's actually a lot straightforward. You can figure out. So that being said, it's fairly easy. These are all the possible values for the 2n plus 4. It starts from 4 all the way to 446. But of course, you only take the even numbers, right? Because 2n plus 4 is actually even number. So how many even numbers you have from 4 to 446? It's actually 446 divided by 2 minus 1. Think about a boundary condition, right? Do not offset by 1. So this is going to be 2, 2, 2. So therefore, how many values for B, C as an integer value? 222. See, this is a very easy peasy stuff, right? Just using the Pythagorean theorem, you will be able to solve the problem very quick. So far, so good? I think this is actually a very easy problem. This is actually using the Pythagorean theorem, right? I'm going to give another problem. We can use some trigonometry, some basic sine cosine relationship, and also help you to expedite your calculation. So it's going to be another problem. So this problem, again, if you check the official solution from Euclid, it's crazy. But my solution is way more straightforward. This is a problem that comes from, let me see the year, is 2018. Euclid, question number 8, B part. So let's have a quick look at it. The problem says in the diagram, rectangle PQRS is placed inside a triangle ABCD in 2 different ways. Firstly, with Q at B, R at C. So basically, these 2 points, they're superpositioning, right? And then second, you just tilt it into the second one. P is here, Q is here, okay? The question says, if AB equals to, this guy, equals to 718, and PQ equals to 250, try to determine the length of your BC. Try to determine the length of your BC. Think about it. How are we going to do this? The only condition give you AB. AB is the side length of the rectangle, right? The other one is PQ. PQ is 250. So therefore, in the first graph, this is also 250. Does it make sense? Right? Because this graph, this little rectangle was actually placed twice. One is this vertically, the other one is actually tilted to here. They're basically the same thing, right? How can I use this to determine the value of BC? The value of BC will be the same value of QR, right? Because QR and BC, they're superpositioning. Trust me, as long as you see such a thing, I think the most straightforward way is actually using trigonometry. Conditional reaction using trigonometry. Using the trigonometry. How can I use the trigonometry? Let's have a quick look at it. So, if this is trigonometry, you have to have the theta or something, right? This is basically what you're trying to do. This is a theta. If this is a theta, this is going to be theta, right? If this is theta, this is going to be theta, right? So that being said means what? You would probably try to denote the value of your BC, maybe using some simple theta, simple trigonometry related stuff. Let's have a quick look. Trust me, this is something so easy. What's the value about DC? DC is dr plus RC, right? What is dr? dr is actually 250 times cosine theta. Is that right? 250 times cosine theta. And what is RC? RC is actually, this guy is BC times sine theta, right? Because, like I said, this guy, RQ, is superpositioning with BC. So BC and RQ, they have the same thing, right? So therefore, RC is BC times sine theta. This is equal to what? 718. 718, right? DC is the same as AB, 718. The other one, what's the value about BC? BC equals to BQ plus QC. BQ plus QC. What is BQ? BQ is actually 250 sine theta. 250 sine theta. And what about my QC? QC is BC times cosine theta, right? BC times, these are so easy, right? This basic trigonometry thing, adding them together, you get what you need. This is your BC. Okay, trust me. Equation 1, equation 2. Let's do a very quick analysis. From equation 2, you can find out BC actually equals to 250 sine theta 1 minus cosine theta. Is that right? This is easy, right? I'm going to use this. You can solve this, right? BC equals to 250 sine theta over 1 minus cosine theta. You have number 3. You just insert number 3 into equation number 1. Insert number 3 into equation number 1. So the BC will be replaced. I'm going to use the color. Will be replaced using the new one, right? So let me try to rewrite it. 250 cosine theta. 250 sine theta 1 minus cosine theta sine theta equals to 780. Is that right? This is an easy one. So 250 cosine theta, 250 sine square theta. Sine square theta could be written as 1 minus cosine square theta, right? It's a basic trigonometry relationship between sine square, cosine square. And this is what? 1 minus cosine theta. 780. This is going to be what? Let's try to do a very quick calculation. Then you'll be able to find out. This is going to be a cosine theta's equation. Right? This is only cosine theta. Let's try to see what can I do. 250 cosine theta equals to 250. 1 minus cosine square theta equals to 1 minus cosine theta 1 plus cosine theta. Minus could be cancelled. Oh, this is nice. 780. So therefore, cosine theta equals to 117,125. Right? As long as you have cosine theta equals to 117 over 125, you plug it here. You know the cosine theta, you can determine sine theta, right? You know cosine, you know sine, right? So sine theta will be equals to 1 minus cosine theta square, then under root. So therefore, you have sine, you have cosine, plug it here, you will be able to get a value of BC, which is 1375. Look, so easy, right? You do not, so basically the most challenging part is you need to write out those two equations. A student got a question. In question 1, do you mean RC equals to QC sine theta? RC, yeah, equals to BC sine theta, not QC. QC, you should use tangent theta. BC is the hypotenuse, right? Because QR and BC is superpositional here, so then you can use BC. Yeah, our lecture, you can just ask any questions. This is an open lecture. So from the second lecture, we're going to go to our regular lectures. Then there's a lot of Q&A sessions. If you have any questions, just let me know. You can post it into the group chat. Some students are a little bit shy. They do not really to ask too much, but it's okay. No problem. You can put it into the group chat. As long as they see your question, I'm going to be able to answer your question right away. So look, you use the sine theta code, use some trigonometry stuff. You're not using any crazy trigonometry, some basic trigonometry. You solve the problem in about a couple of lines, right? I want to show you the process. I'll give you a little bit more details. If you see the official solution from Euclid, it is crazy. I'm going to give you the question number 2. Look. This is the official solution from Euclid. It used a lot of weird things. I don't know what they're talking about. There's a lot of complicated calculation here and there using this. It's total, and also a bunch of like similarity things. I don't know what they're talking about. This is too much. You won't be able to do it. So try to use my way to simplify your calculation significantly. Okay? So our lecture is trying to teach you the quick way, the fast way how to do stuff. The Euclid official solution is way more complicated. You do not really have time. Like I keep saying, if you just copy the question, 2.5 hours, and then it's not good enough. Not to say you think of the solution in 2.5 hours. So you always have to learn some faster way, try to do the problem. All right. Yeah, I think we're running out of time today, so I don't want to keep you guys for too long. But generally speaking, I think we covered first 2 halves, right? First 2 categories. The first category is the area. We teach you guys 3 different ways, try to do the calculation. The second one is using some simple, straightforward theorems, try to do the problem. We talk about the Pythagorean. We talk about using some sine, cosine trigonometry, right? So these are something very intrinsic and very basic. You're going to see them very often from time to time for the Euclid math competition. Try to use some easier way to expedite your calculation process. And we actually have a third one. Try to use the similar triangles property. Similarity is perfect square equals to the area method. We can talk about in our next lecture because we're kind of like running out of time. But generally speaking is that our lecture actually offers 2 ways try to prepare the Euclid. One is actually using our bootcamp. Try to take everything together, give you all the concepts one after another. Well, the other way is actually using our crash course courses. So give you some simple problems, but teach you guys what is the expedited way, try to solve them. So either way, these 2 things will be collaborate together to give you guys a better way how to do the Euclid problem, how to understand those tricky things from all over the places. So the last 3rd question. Yeah, a student said, can I see the last 3rd question with the square? Yeah, no problem. If you're registered in our lecture, I'll be able to send you the entire course. So you have the full access for everything. So no worry about it. Let's focus on the most important thing. And also our lecture offers some free lectures. So this is the WeChat. So you guys can take a screenshot and then ask your parents if they're using WeChat to talk to my assistant. And she will be able to provide you the 100 hours free lectures about how you learn the basic concepts, how you learn all the technologies, so on and so forth. And they'll be able to help you out for the Euclid math competition. Okay. A student got a question. For the questions you showed us at the start, do you recommend that we try to understand the proofs? So you mean the first question talking about the rotation, right? Yeah, definitely. All those kind of the rotation problems that are very important. You need to understand it. Yeah, I think that's pretty much what I want to say for today's lecture. You can actually take a screenshot for this WeChat. So our assistant is going to be able to send you the detailed free lectures upon request. And I think that's pretty much what I want to say for our first lecture. Our first lecture is just give you guys a quick overview of what we're going to be covering for this 10 lectures. We're going to use these 10 lectures to basically cover the most important concepts for the Euclid and to give you guys the concepts, the most important types of problems, and how to solve the problems. The samples, the problems, and the categories working together is going to be able to help you out for the entire process. Okay, student got a question. How do we understand the proof of Stewart, Menelaus, and CVAR? For Euclid, not so important, but for AMC and AIME, definitely yes. Yep. Any other questions? Are we all good? So hopefully you enjoy our lecture. And what is the year of the last question coming from? The year of the last question should be coming from 2018. 2018. All right. Any more questions? How can we ask for questions outside the class? You can always, if you register the class, you can always talk to me. Our lecturer offers unlimited office hours. Any questions, talk to me. I'll be able to help you guys out. You can, like I said, if you want to have any questions, you can scan this WeChat barcode, this kind of like a QR code, ask your parents to contact our assistant. She will be able to help you guys in the registration. And you can, yeah, for these entire lectures, if you're registered, we have like unlimited office hours. Any questions you can ask, we'll be able to provide you a very detailed, comprehensive solutions. Okay, any questions regarding Euclid? I missed the deadline for payment. Can I still register? Of course, yeah, it's still for the registration. Our course is still open for registration. You can contact our assistant, or if you're in the group, in the WeChat group, you'll be able to ask for the payment. We'll be able to process that. Yeah. Any other questions? Post it into the group chat. We can always help you out. So having a good understanding how the Euclid is organized and the way about the lectures to be covered is crucial. Euclid is very similar to AMC, but still have its own varieties. So our lecture is actually offering the insights for the specific Euclid. All right, I don't see any new questions coming out from the group chat. I wish you guys a good day, and hopefully you enjoyed today's lecture. Okay, one more question. Yeah, you can type it into the group chat. I can wait you guys for a few more seconds. So yeah, that's the way how our lecture works. And yes. Okay, any more questions? Can we claim the replay of the lectures? This is okay. Yes, if you registered, we can provide the replay of the lectures for sure. Yeah. All our lectures have the lifetime replay. You can talk with the assistant. They will be able to provide you during your registration. We provide a lifetime replay for all the lectures, everything you learn after 20, I don't think after 20 years, after 1 or 2 years, you can still replay them. It's like Udemy, right? Udemy, as long as you registered, all your lecture will be there available for a lifetime. Okay. Okay, if there's no more questions, I wish you guys a good weekend. And yeah, you can ask for Alex, same thing. Yeah, and hopefully you guys have a nice weekend and good luck for our upcoming Euclid math competition. Bye. Bye, guys. Have a good one.
Bye. Take care.
Bye.